Hello and welcome. Gradually, the semester is coming to an end as far as teaching is concerned. So today we are going to focus on session 5 of this semester's program. You realize my presentation is a bit new this time round. I keep trying new things every day, and I expect you to also make time to do same, just to improve yourself. Yeah, so from same recording venue, but with a bit of a change in the background. Something I've been trying for a long time, but I guess I'm gradually getting there. Still using my phone, that handset, as my camera, and then the rest is my computer. If you're using Vmix for this week's work, I must inform you that you need decent graphics, NVIDIA graphics or AMD graphics, anything in the range of GTX 1660, 1620 Super, 1660 Ti. I mean, pretty much if you have such graphics, you'll be fine. But I will encourage you to be using any of these tools I've recommended for you on an Intel graphics. It may compromise on your video quality. Some of what I've done right now, your machine may struggle to pull them off. Even this machine, I don't vouch for it so much. I just know I can push it to a certain threshold. All right, so let me know your impression about this new approach for this very last session. I would love to hear your comments. Right, okay, so as I indicated, we are going to focus on session 5, sorry, beg your pardon, for this particular session, and so we will hit the nail on the head. Session 5. So we're going to talk about software evolution and dependable systems. Software evolution and dependable systems. We softwares as has been developed since the late the late 1980s down the line till today are not the same things anymore. In the beginning of this lesson, we were discussing how waterfall model was at its prime back then, but today we rarely even discuss waterfall because of the changing nature of businesses. Facebook, for example, I don't know how many of you were signed on to Facebook when they came out publicly in 2007. Now, if you have been an active user, you would attest to the fact that it has changed over time. It's not the same Facebook interface and features and dynamism you've been experiencing back in the day that you still experience today. Technologies have evolved, and that is the word we use there. So software evolution and dependable systems. You don't just engineer solutions and leave them just to fly, but they must stand the test of time, and we need to discuss the evolution of softwares. Now, this at the back of your mind as a software engineer. It goes a long way to influence how you come up with your eventual solution for your clients or for any organization you may be engaging with. So let us look at the big picture. The point is that there are many reasons why software change is inevitable. New requirements are emerging every day, when a software is being used. And as I made mention of earlier, business environments continue to change. Okay, so these instances requires that we discuss software evolution. It has to be part of the conversation. When errors evolve, we must repair them. And when new computers and equipment are added to the system, we must do same. At the time of this recording, Apple had released their new M1 Pro and M1 Max chipsets in their new 14-inch MacBook Pro and then the 16-inch MacBook Pro, and the price is somewhere else. Not too long ago, barely 2 years down the line, their machines were running on Intel CPUs, but now they are on what they refer to as the silicon chips. So if you have followed this conversation keenly, it's not like I'm a fan of an Apple, or neither am I an Apple user. I just have an iMac on my desk in my office. Most of my equipment is Windows, but we follow the news. So we still have a number of applications that have yet to make transition, to run smoothly on these new ARM chips, or what they refer to as the silicon chips, regardless the power packed in there. So these are some of the realities we need to come to terms with. So if you belong to an organization and computers are facing off, you were once using Windows and we need to replace them, as far as evolution is concerned, we need to add to the conversation when such instances occur where new computers and equipment are added to the system or replaced. So that is the bigger picture. Another point is that the performance or reliability of a system may have to be improved generally. We may not be encountering errors or any of the previously mentioned motivations to consider software evolution. Now, the key problem of organizations is implementing and managing change of their existing software systems, and that is one point that we need to come to terms with. So still on the big picture, we're saying that organizations have huge investment. They have very huge investments in their software systems. They are critical business assets, and we cannot ignore that fact. So to maintain the value of these assets and businesses, they must be changed and then updated as time moves on. And the majority of the software budget in large companies is devoted to changing and evolving existing software rather than developing new ones. Okay, so they just want to meet the test of time and not necessarily scrapping off everything. Of course, there are instances where some organizations just scrap off everything completely and bring a whole new service, and it has its own challenges. So we have a spiral model of development and evolution that represents how software systems evolve through a sequence of multiple releases. So we can look at it like this. We have over here. So we start from the specification. We have the release 1, release 2, release 3. We need to appreciate the specification, the implementation, validation, and then the operation. So that cycle moves in that particular order, and we repeat this iteratively. Okay, so let's look at the process into detail as far as evolution is concerned, shall we? All right, so let's look at the evolution process. Now, software evolution process depend on the type of software being maintained. It depends on the development process, and it depends largely on the skill and experience of the people that are involved in here. So there could be proposals for change that are driving this, which is the main driver for software evolution, and this must be linked with the components that are affected by this particular change. So it allows cost and impact of the change of system to be properly estimated, and that's the point we're trying to drive home here. So you need to identify the change and then allow the evolution to continue throughout the system lifetime. Okay, so we use this diagram to depict exactly what we are talking about. So we have change requests, okay, then we have the impact analysis, and then we look at the release planning. In the release planning, we have fault repair, platform adaptation, system enhancement. These are points that needs to be considered. These components must be factored into the whole process, so that when you have any of the constraints we anticipate, you have the structures in place to deal with them without any hiccups. So once you phase out the release planning, then you can change the implementation depending on the outcome, and then the system release can take place. And like we said, because it's continuous in the lifetime of a whole what we call a system, this process repeats itself over and over again as long as the organization remains in operation, and we need to acknowledge that. So what do we mean by the change implementation? Now, change implementation can actually be viewed as an integration, as an iteration of the development process. Okay, so you have the revisions of the system that are designed, implemented, and they are tested. A critical difference is the first stage of change implementation that may involve program understanding, especially if the original system developers are not responsible for the change. that is likely to happen. So during the program understanding phase, you have to understand how the program is actually structured and how it delivers functionality, and how the proposed change might even affect the program. Is very, very important. Then you are acknowledging this particular stage. So agile process comes in handy, and they are based on incremental development, because that is what we have been discussing all this while. So the transition from development to evolution is actually seamless if we consider software evolution process. Okay, so what we literally imply by this evolution, and that's why we've highlighted those portions, it is the continuation of the development process. So in practice, what my team and I used to do when we were engaging with clients, and as I consult periodically from time to time, is that beyond the deployment of the solution after we have developed everything and gone into production, we have another period of maintenance that we include in the agreement that we sign, the business consideration that most of you have put together to have some agreement with your clients. It becomes important so that within at least a period of 12 months after the production phase, you can hang on and update and tweak portions that might not have been seen, errors you might not have detected, if there need to be some improvement. All of these things phase in, so we include that and add that to the costing of the whole project. It becomes quite essential, but that is just one side of the story that I'm mentioning right now. So there is a continuation of the development process, and it's based on the frequent system releases. I'm pretty sure you have checked the number of versions of Zoom applications that are out there so far, the number of versions of Facebook that have been released ever since. It seems that almost every day there is a new update. It's just that nowadays most of you don't even take notice of it, because your phones automatically, once they have internet connectivity, they update themselves. But that's the reality on the grounds. So automated regression testing is actually particularly valuable when changes are made to a system, and these changes may be expressed as additional user stories. Once you consider them in that way, it becomes easier to consider these processes and then include them as and when the need arises. There are program evolution dynamics that we need to acquaint ourselves with. Basically, what we are trying to say is we are trying to study processes of system change. The study of processes of system change is what I refer to as the program evolution dynamics. So the system requirements are likely to change anytime we have this evolution triggered at one point in time, and while the system is being developed, because the environment is actually changing. So when this happens, a delivered system won't meet the previous requirements. New ones take center stage. So systems are tightly coupled with their environment. So when a system is installed in an environment, it changes that particular environment, and therefore this also changes the system requirements. So the system must be changed if they are to remain useful in a particular environment in which they are being deployed. So after several major empirical studies, we can talk about Lehman and Beladi. You see all of this in the key text. Now that I've mentioned the key text, another issue my attention has been drawn to the fact that quite a significant number of you have resolved not to make time to read the key text. Time has caught up with you. I can evidently vouch for a number of your colleagues who have diligently actually made a conscious effort to cover the key text. And so watching this video is only a compliment to what they have read. And so the highlights that I present only buttress and clarify some of the points they have exhausted by way of reading. It's rather unfortunate, but my attention has been drawn to the fact that a significant number of you would prefer to get yourself overwhelmed with other, excuse my choice of words, but unnecessary personal engagements, and then you conclude that the key text is voluminous, there is no time to read, etc., etc. And that is clearly showing in much of your results as it turns out in the assignment. But I can't help it. What you earn, I'll give to you. So if you won't read, I'm happy there have been impacts on the significant number as well. Okay, because some of your colleagues had even exhausted the reading of the key text and walked up to me wanting to know more. And fortunately for them, this course project has been an eye-opener and a compliment to the course in a way they didn't even anticipate. So the likes of you who feel it's a race against time, somebody's comment was even the fact that why is this course reading course and this man has turned it into a project? He suddenly has found some practical he has added to it. When that comment reached me, I smiled. I'm not going to mention names. I'm pretty sure if you are watching this, you probably be wondering whether your friend has betrayed you. But it's not betrayal. That's why I'm not mentioning names. It's a point I'm trying to drum home here. So you would have preferred just reading and then chewing and pouring and answering some questions. I might as well have recommended that. Why did you come and waste your time in IT or computer science? It wasn't compulsory to enroll. So you might have as well stayed off this particular course than to rather join and then be making and passing unnecessary comments that are not useful. If you have any comments, you keep them to yourself. But those who are benefiting largely and greatly, they know. Okay, and so let's keep the flow. Let's keep the flow. All right. So as I was saying, if you have read the key test, these are detailed references in it. Okay, so there's been empirical studies, facts, research has been conducted, and there are figures to support and back these submissions. So Lehman and Belady have proposed that there are a number of laws which apply to all systems as they evolved, and there are sensible observations rather than laws. There are sensible observations rather than laws, and they are applicable to large systems developed by large organizations. So what are some of these laws and their descriptions? Quite a number of them have been outlined and bulleted, but we cannot go through all of them. We have continuing change, we have increasing complexity, we have large program evolution, we have organizational stability, we have conservation of familiarity, we have continuing growth, we have declining quality, and of course feedback systems. And these laws have been described into detail over there. So this will be just about the evolution dynamics. We can also talk about the software maintenance. Not that we should actually talk about the software maintenance. Maintenance actually focuses on modifying a program after it has been put into use. As simple as that. And I already made a submission about this when I spoke about the fact that development process is a continuation as far as evolution is concerned. So this was the point I was trying to drum home here. Modifying a program after it has been put to use. So when our client's solution we are in production mode, we also have room for maintenance for at least a period of time before, if we have to wash our hands off them completely, we proceed to do so. So the term is actually mostly used for changing custom software, and generic software products are said to evolve to create new versions. So maintenance does not normally involve major changes to the system's architecture. No, changes are implemented by just modifying these existing components and adding new components actually to the system. So there are various approaches we can get this done. We have maintenance to repair software faults. Okay, so you just change the system to correct the deficiencies that you identify by in a way to meet the requirements of your clients. And then we have the adapting of the software to a different operating environment. So we are changing just the system so that it operates in a different environment. It could be an operating system like we discussed with the new Mac chipsets and so on and so forth. And we have maintenance to add to or modify the system's functionality entirely. And by this we are modifying the systems to satisfy probably specific new requirements. So these are some of the things. like I mentioned, it doesn't come cheap, so you have to cost it. Maintenance costs are usually greater than development cost. Usually 2 times to 100 times, depending on the application. That's how much it can cost, and they are affected by both technical and non-technical factors. So usually they tend to increase as software is actually maintained, and maintenance corrupts the software structure, making further maintenance even more difficult. And so that is a reality we must acknowledge. You cannot be oblivious over that. So aging software can actually have high support costs. We're talking about old languages, compilers, etc. I was telling some of your colleagues some time ago that the application I developed as my undergraduate project work, in an attempt to pull my codes again, at the time I uploaded them in 2009 onto Google Drive. I even exported my database from the MySQL, MariaDB, and added it in a zip file. It's there, I can see it, but they won't let me pull it. They said the scripts contain some malicious blah 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 codes that could do what. So it's still hooked up with them. Maybe someday I'll find time to pull it some way, somehow, I don't know. But the point we are trying to drive home here is times have changed, the codes have changed, languages have changed. What was previously accepted, now they are telling me is, contains viruses and malicious blah blah blah. So these are realities when I talk about aging softwares, and all of these things add up to costs. So we have some factors that goes into maintenance. We have team stability. Those who were involved in the project may not be the same people there, and there's one critical challenge of what do you call it, companies, software development companies, because you have a team you have started to work with over a period of time. Probably even the lead developer will tell you that I have resigned and have joined a new team. You have already deployed solutions for clients. How do you sustain this? How do you maintain this for your clients? How do you even find the same fit to come and fill the same shoes? So team stabilities, all of this comes, they add up to the maintenance cost. We have contractual responsibility. So the developers of a system may have no contractual responsibility for maintenance. So there is no incentive to design for future change. Some clients want this the cheap way. You are yet to encounter most of them, but brace yourself. And we have staff skills. Maintenance staff are often inexperienced and they have limited domain knowledge. So these are other realities we must come to terms with. So if we have to recruit somebody else, other people with the needed set skills, then the money must talk. And we have program age and structure. As programs actually age, their structure is degraded and they become harder to understand. The beginning is not the React today. Laravel, as Facebook put out there, over PHP is at a different level today. So we cannot ignore the fact that changes are occurring. Right, so this is maintenance cost. We can also talk about maintenance prediction, which is concerned with assessing which parts of the system may cause problems and have high maintenance costs. You should be able to predict the number of changes, and predicting that requires predicting the number of changes requires an understanding of the relationships between a system and its environment. Okay. So there are factors that influence the relationship between the system and its environment. We have one, the number and complexity of the system interfaces, the number of inherently volatile system requirements, and then the business process where the system is actually used as well. So what goes into this whole process of prediction? We need to maintain predictions, and it can be made by assessing the complexity of the system components, or the components that we discussed earlier. Research has been invested in this direction, and it has shown that most maintenance effort is actually spent on a relatively small number of system components. So it will depend on the complexity of control structures, it may depend on the complexity of the data structures, and it may depend on the object or the method or the model size. All of these things we have discussed at length in the previous sessions. So if they are going to be measured, or if we are going to access and measure all of these things as we have made mention of, then what are the process metrics? These metrics may be used to assess this maintainability. So if any or all of the if any of them, everything that we've spoken about, any of the factors we have even made mention of earlier, if these are all increasing, then it may indicate a decline in maintainability. So let's look at some of them. If the number of requests for corrective maintenance is increasing, if the average time required for impact analysis is also increasing, if the average time taking to implement a change request suddenly starts to appreciate, the number of outstanding change requests is also appreciating, then it may indicate a decline in maintainability of the particular system. Great. Right, so let's talk about system re-engineering. Another topic we need to drum home here. When you need to restructure and rewrite either part or all of your legacy system, however you still want to maintain the functionality of the application, it becomes necessary to re-engineer your solution. The system may be restructured and redocumented, and it has several advantages. You're able to reduce risk and you're able to reduce cost in the process. What processes goes into this? We have source code translation. We convert the code into a new language. We have reverse engineering. So when you get to the industry, you should know how to use these terms appropriately, in their right forms. Analyze the program to understand it. Program structure improvement. You restructure the system automatically for your program. You restructure it automatically for understandability, program modularization, reorganize the program structure, and of course data re-engineering, cleaning up and restructuring the system data. These are common practices out there. Now, this word I came across for the first time when I was in industry, and I would confess it was in the industry I heard of this word for the first time. I call it refactoring, and it made a whole lot of difference in my understanding and knowledge in software engineering. And so I'm happy to share it with you this time around, that I have the opportunity to pass on knowledge. The mere process of making improvements to a program, to slow down degradation through change, we use the word refactoring. So you can think of refactoring as a preventative maintenance, which reduces problems of the future. So it involves modifying a program to improve its structure and reducing its complexity, or making it easier to even understand. So literally, when you refactor a program, you should not add functionality, but rather you concentrate on the improvement of the program. So re-engineering takes place after I'm borrowing words from the words we just defined in the previous slides. So re-engineering takes place after a system has been maintained for some time and maintenance costs are beginning to soar. So you use automated tools to process and then re-engineer the legacy systems to create new systems that is more maintainable. So refactoring actually is a continuous process of improvement throughout the development of the evolution process. It is very, very important. It does what we refer to as a bad smells of code, that are stereotypical situations in which the code of the program can be improved through refactoring. So we have duplicated code, long methods, duplicated codes, code that may be included at different places in the program, and it can be removed and implemented as a single method or function that is called as and when it's required. We have the long methods that should be redesigned as a number of short methods. At this point, we are talking object-oriented programming here, so I expect you to follow this conversation. Switch or case statements, I'm pretty sure you came across them during your control structure study in your programming 1 or even in C++, fundamentals of programming. So it's an alternative to if, else, why. I'm pretty sure some of you have remembered these things, right? So, they often involve duplication. So where the switch depends on the type of value of the switch statement may be scattered around the program. We need to consider that we need to have that at the back of our mind as far as this duplication is concerned. So in the object-oriented programming, you can often use the polymorphism concept to achieve the same thing, right? Then we have the data clumping, which occurs when the same group of data items will occur in several places in the program. Okay, so these are vast amounts of code that are stereotypical situations in which the code of a program can be improved through refactoring. Then we have the speculative generality, which occurs when developers include generality in a program in case it is required in the future, and this can actually simply be removed, right? So that is about that. So what is the legacy system management entirely? I mean, as a subject, organizations that rely on legacy systems must choose a strategy for evolving these systems. We have legacy systems. Okay, so the chosen strategy should depend on the system quality and its business value. So we can talk about a consideration for low quality, low business value, and this should be scrapped. We have low quality, high business value, we make an important business contribution, but these can be expensive to maintain, so they should be re-engineered or replaced if the system is available. In events where you have high quality, low business value, you replace the cuts and then you scrap completely or maintain. These are your options. If we have high quality and high business, come on, continue the operation using your normal system maintenance. So that's the chart on the side of this statement too, just to give you a picture of exactly what we are talking about, right? So this is about legacy system management. In the next video we'll talk about dependable systems, and then we'll wrap up for this particular session.